Okay, so this week there's a holiday on Friday, so this time I'm gonna just record some videos on how to do some of these problems. And for this set, this is a light set for this week, and there are 5 problems: sticky case, pot, square peg in a round hole, long checksum algorithm, and permuted arithmetic sequence. So I'm going to go through each of them. I'm not going to spend too much time talking about the problem themselves. I assume that you can go and read the problems, but I'll talk about my solutions. All right. So first one is sticky keys. Basically, you're given a string of characters. The string can include spaces. That's important because that means that when you read the string, if you just use the extraction operator CN with the 2 greater than signs, it will skip the spaces. So you have to use something like getLine. And then the string is at most 1,000 letters, so it's not very big. And what you're supposed to do is to remove consecutive duplicate letters. So if you see a bunch of letters that are the same, you have to shrink it down to just 1 copy. But letters that repeat but not consecutive, you don't touch. So that's the summary of the problem. And there are many ways you can do this. You can write a loop to go through and check consecutive letters. What I would like to say is that it's probably harder for you to try to physically remove characters from the string, because erasing things can shift indices and can screw things up in your loop. It's much easier if you just form a new string that has only the letters that you want. Having said that, if you know how to do this quickly in using system library, then that's a lot faster. So that's what I did in this piece of solution here. First, I read the string getLine. Remember, use getLine. And then I use this function called unique. It's an str algorithm that it's meant to remove all the duplicate elements in the container, provided that the container is sorted. Now, I did not sort this container because I don't want to change the order of the letters. And I'm using the feature or bug or whatever you want to call it, that if you don't sort the container, the unique algorithm actually will only remove all the things that are consecutive duplicates, which is actually what you want. And then the other thing that you have to know is that unique, if you read the documentation, unique actually doesn't actually change the size of the container. It just moves things to the beginning so that there's no duplicates, but it will return an iterator that points to the end of that chunk. So what you have to do if you want to resize it is to take the iterator that it returns, subtract from it the beginning of the container. That will give you the actual number of elements in this list that it's that has the duplicates removed. And then when you call resize with that new size, now you will actually shrink the string to contain only the elements that you want. And then of course you just print it out, and that's the end of the program. Now you don't have to use this if you're not familiar with this unique and resize and all that stuff. You can just write a loop that goes through each character. So your first character, you always print it out. And then for each other character, if the character is different from the previous one, then you print it out. So there are other ways you can do this. So for example, you can say cout, print the first letter, always. And then for I, go from 1, not 0. I less than s dot length, I plus plus. If si is not equals to si minus 1, then you print it out. And then at the end, you print a new line to finish the output. So that's another way of doing it. Okay, so that's the first problem. So the next question is called pot. And the idea is that you have a bunch of numbers that you're trying to add, and they'll tell you, 212, 1,253, and so on. But what they're telling you is that 212 actually means 21 raised to the power of 2. This actually means 125 raised to the power of 3, etc. So the last digit is the exponent, and then the first part of this, except the last digit, is the base. So you have to raise this to a certain, basically take each of these numbers apart, do the appropriate exponentiation, and add things together. Now you might, if you think a little bit about this, it says that there are at most 10 numbers, and each number is between 10 and 900, 9,999. So if it's 9,999, it's actually 999 raised to the power 9. And that's its problem, because it can overflow a normal 32-bit integers. But when you read the output, they also tell you that the original output, it's no more than 1 billion. And that's well within a 32-bit integer range, because the 32-bit integer will have a limit of about 2.1 billion. So they're telling you basically that you don't have to worry about overflow. So that's good, because now we don't have to worry about that. So all we have to do is figure out for each of these numbers how to take it apart and how to exponentiate. And the first thing is, how do you take it apart? Well, you use the mod 10 and divide by 10. When you do integer quotients, divide by 10, you get rid of the last digit. And when you do mod 10, you get the last digit. And then the next question then is, how do you actually do the exponentiation? If you have heard me talk about this before, the answer is do not use the power function. Write your own. And because the exponent is so small here, I can just do pretty much anything. I can just do a loop that multiply b by itself n times, and that's good enough. And make sure that you initialize the 1 for the case when the exponent's 0. If you have much bigger exponent, there's a fast exponentiation algorithm that takes log n time, but for this problem, it really doesn't matter. And it's so small, and it's one single digit, so it's at most 9. So it doesn't really matter what you do. So that's pretty much it. So the main trick is to know how to take it apart, and then also how you compute the exponents. All right, let's look at the third question. This one is a little bit more involved. Actually, maybe I'll skip it to the next ones first, because maybe the other ones are a little bit easier. I want to get rid of this box here. Can I get rid of this? Okay. Move this a little bit further. Okay, so let's look at this lunch checksum algorithm. Basically, you're given a sequence of digits like this, and then they give you an algorithm that says that you start from the right end, and every second digit, it's multiplied by 2. And then if after you multiply by 2, the answer is more than 1 digit, then instead you add the digits together to get the single digit. So basically every second position you do this transformation, and then after that you add up all of the numbers, and if the resulting number is divisible by 10, it passes, otherwise it fails. So basically all you have to do, the first thing is, you have to realize that these numbers can be really long. It says that each one can have at most 50 characters, so you cannot actually afford to read it as an integer. But if you just read it as a string, that's good enough. And then you have to go around, and every single character, every single digit, you have to convert the character into digit value, and then either you add it or you add 2 times of it. And then there's the other problem of what if it's bigger than 10? bigger than or equal to 10, you have to deal with that issue as well. But anyway, you can do that. You add it all up and then you see is it divisible by 10. And that's pretty much it. The only thing that you have to be worried about is that this process is starting at the right end. So if you start at sometimes it's easier to start at the left end because when you write loops, you go I equal to 0 and up. We're starting at the right end, you have to go from, if you're looking at the string index, you have to actually reverse it, right? You have to go from the length of the string minus 2 and then go backwards. But other than that, there's not much to this problem. So I'm just going to quickly switch to the code. And there are multiple test cases. So I like to usually write this like this, that I read the number of cases and then I just loop and call a function that solves each case. You can, of course, write this nested inside this for loop, but the fewer levels of indentation and nestedness, the easier it is to understand the problem. So I usually like to do separate the code to solve each problem, each instance test case is its own. So here it is. So I read the string. I have a sum that keeps track of what I'm adding up. And this is a little trick. As I said, you have to loop backwards, but another way to avoid that is to actually reverse the string first before I loop. So I'm actually just reversing the string, so I don't have to think about looping backwards. And if I reverse the string, then I can loop forward. Then for each character, I use the trick of subtracting the ASCII value of 0 to get the decimal value. And then if it's odd, so this is the every second part, I would multiply by 2. And if it's bigger than 9, then I break it into basically the 2 digits. So again, it's the same trick. Divide by 10, mod 10, those give me the 2 separate digits, add them together. And no matter what happens when you multiply a number, when you multiply a single digit by 2, the biggest it can get is 18. And then when you add the 2 digits separately, you can never be bigger than 10, bigger than or equal to 10 again. So you don't have to worry about doing it in a while loop. And then once you've done that, either you have gone through this process of doubling or you haven't. In any case, I'm just dividing by adding the d, and then I divide by 10. Now you don't have to divide by 10 at this stage. This is remainder divided by 10. You don't have to divide by 10 right now. You can divide by 10 at the end, provided that things are not going to overflow on you. And for this problem, I believe the limit is 50 characters, and each character contributes to a sum, at most 9. So you're safe. But if you have to worry about whether it's going to overflow, if all you care about is the remainder, you can actually divide by the divisor at any time, and it's not going to affect the remainder. So this is a little trick of modular arithmetic that you might have learned in 1820. You can take mod anytime you want. So that's what I do. And then at the end, if the sum, so if the remainder is 0, then I just print pass, otherwise I print fail. That's this problem. All right. Problem E, permuted arithmetic sequence. So basically what they do is they give you a sequence of, there's 3 cases. The first case is a sequence of 5 numbers. These are the 5 numbers. Second case, it's a sequence of 3. And these are the 3, etc. Each sequence, they're going to give you no more than 100 cases. Each sequence is no more than 100. And then at least 3. And the values in the sequence, these integers are basically between -1 million and +1 million. So there's no real danger of overflow from most things that you do with addition and subtraction. All right, so what is the question? The question is, you want to know if it forms an arithmetic sequence. What does that mean? That means it's a list of values where the difference between consecutive values is always the same. Okay, so for example, 3, 7, 11, 15. It's a is an arithmetic sequence because the difference between two consecutive ones are 4 always. This next one, this difference is minus 10, so that's also an arithmetic sequence. But then 2, 4, 7 is not, because the difference is 2 and 3, it's not the same. And then the other ones, 3, 6, 9, and 6, the differences are either 3 or minus 3. It's not the same all the time. So what are you supposed to produce? For each sequence, output a line that says arithmetic. If it's an arithmetic sequence, so that's not too bad. But then it says output permuted arithmetic if the sequence can be reordered to make an arithmetic sequence. Okay, so you have to figure out if you can reorder something, and otherwise you print non-arithmetic. So how do we know whether a sequence is arithmetic to begin with? Well, if you have an array and whatever number it is, 0, 1, 2, 3, up to n minus 1, all you have to do is you have to look at the consecutive differences and see if they're all the same, right? And you're told that n is at least 3. So what can you do? You can first say if it's equals to a n 1 minus a0. This is always going to work, because when I say this is always going to work, what I mean that these things are always in bound. You're never going to look at a bound. And then you just basically say for int I equals to 2, I less than n, I plus plus, if diff is not equals to a I minus ai minus 1, then return false. Let's say this is a function that takes an array, an n, and decide whether this is a arithmetic or not. And then if you've gone around and everything and you haven't found the difference, then you return true. And this is how you can decide if a particular sequence is arithmetic. Okay, so we can call this function, if it's arithmetic, you print it. That's easy. What about permuted? Well, if you want to permute something to make it arithmetic, if it's not arithmetic already, then basically it has to be either increasing or decreasing. It has to be sorted order. Why? Because if this, let's say if this difference here, it's positive, that means that a1 is bigger than a0. And if the difference is the same, then a2 has to be bigger, and so on. Of course, if the difference is 0, then that's everybody must be the same. And if the difference is negative, it means that your arithmetic sequence must be decreasing. But you actually don't have to worry about that case, because we're allowed to permute things. So if it's decreasing, it's an arithmetic decreasing sequence. If you reverse the string, if you reverse the sequence, it will become an increasing arithmetic sequence. So basically all you have to do is you have to sort the array from smallest to largest, and then call your arithmetic sequence check function. And if it returns true, that means that this is a permuted arithmetic sequence. And so that's the basic idea. So let's go to my code. So I have a function that checks if it's arithmetic. So I'm using a vector, and you can use an array if you want, doesn't really matter. And I compute a difference, and I guess I could have started this at 2, but because I'm using I plus 1 instead of I plus 1 minus I instead of I minus 1. So I start at 0 and I end at 1 before, so I don't go out of bounds. But otherwise, the code is what I wrote. And then over here, I read in the, so this is solve. So I use the same structure. I read a number of case, and then I loop over the number of case and call solve. So what do I do with solve? I read in the number of elements, and this time I use a different way of reading just for variety and showing you different ways of reading stuff. So first I allocate a vector and I initialize it to I initialize the size to m because I know what the size is. Then I use a loop. This is what is called range space for a loop. It loops to all elements of the vector v, and it's passed by reference. So when I do c and x, it will actually stuff the input into every element of the vector one at a time. And then I do basically what I just said. If I call arithmetic and it says it's true, then I say arithmetic, end of story. Otherwise, I sort and I call arithmetic again. And if it's true, then I say permuted arithmetic. And if it's not arithmetic, even after you sort it, then it's non-arithmetic. And those are the three possible outputs. Okay, so now I'm going to go back to this one that I skipped in the middle, square peg in a round hole. So there's this NMK and then there's RISI, but what's everything is between 1 and 100. So I'm just going to very quickly say what this problem is. You have a bunch of plots. They are circles of various radius. 0, 1, 2, and so on. So you're given a list n of them that have these plots. You're given m circular houses that you want to build, which also has their own radius. Okay, there are m of them. And then finally, you have a bunch of square houses. And they also have different sizes. And the k of them, and with these square houses, you're given a side length. And so on. What you want to do is you want to put houses, whether it's circular or square, into these plots. And you want to put as many houses as possible. Okay. What's the constraint? The constraint is that when you put a house into a plot, the house cannot touch the boundary of the plot. So the house has to be somehow strictly smaller than the plot. All right. So that's what we're talking about. So there are a couple of things. So first of all, does a house fit in a plot? How do you determine this? Okay, circular house is easy. If your house has radius r, let's call it RH, and your plot has radius RP, so you have a radius RH and RP. How do you know if which fits? Well, RH has to be strictly less than RP. If they're the same, it fits perfectly, but you're not allowed to touch, so that's no good. And of course, if RH is bigger, you can't fit. Okay, that's the easy one. Square, it's a little bit harder. So what I want to SH and then RP. Well, if you put the square in a circle and it just touches, that means that this diagonal, it's exactly 2 times the radius. So this diagonal, it's 2 times the radius. So the diagonal is SH square plus SH square root using Pythagoras theorem. And then the diagonal, it's also 2 times the radius. And it has to be strictly less than the fit. But we generally don't want to take square root because there can be round off errors. So what do? Instead, we square both sides. So actually, I don't, I can actually simplify this as 2 sh squared less than 4 times rp squared. And in fact, I'm going to just square everything. Everybody's squared. And this is a trick that you can use to avoid taking square roots. So if 2 times sh of the side length squared, it's less than 4 times rp squared, then it fits. And if you want, you can even simplify that by removing the 2 on each side and factor that, divide it out. Okay, so these are the two checks that you can use to decide if a house will fit inside a plot. Okay, but now there's another problem. The problem is not just which house fit in where, but how do you actually assign the houses to the plots? Because if you assign it the wrong way, maybe you end up wasting a lot that no other house can fit in. So basically now what happened is this. You have a bunch of plots, and let's order them from biggest to smallest. Okay, and then you have a bunch of houses. And I think now, actually, I don't even care if it's a square house or a round house anymore. Why? Because if it's a square house, if it's a round house, circular. If it's a circular house, then I'm going to look at the house square. But a square house, actually, I can pretend it's a circular house with what? So actually, let me just multiply both sides by 2 so it looks the same. So with a circular house, I pretend that the radius is 2 times rh squared. And this square house, I can pretend this is a circular house with radius sh squared. Well, radius square anyway. So I can actually pretend like this. So square house, I can pretend to be circular house. So all of them are circular. So the houses would look like this. Let's say. And I'm drawing them like this because I think what I'm going to do is I'm going to sort them in order from smallest to largest. Okay, why? If I take this house and I try to fit it, well, intuitively, I want to fit it into the smallest plot that I can fit it in. Why? Because if I fit it into something bigger, now this plot may not be able to be used by a bigger house, and now I just kind of wasted it. So the trick here, and I'm not going to prove it formally, it's used what is called greedy algorithm. For each house from smallest to largest, I'm going to fit it in the smallest plot that I can fit. Okay, so maybe there's even smaller plots like this. So I'm going to skip over these. And why? Because if I cannot fit the smallest house into these ones, and all the rest of the houses are bigger, then clearly nobody can fit into these plots. I can ignore them. So I fit it into the smallest plot I can do. Now I do it. And then I just keep on going. And then maybe at some point, some I have to skip further because some plots are too small. And eventually I either run out of houses or run out of plots. And then I just keep track of how many houses I successfully assign. And that's basically the way that I write my code here. Now I didn't bother dividing by 2 in my square inequality, so I multiply everything by 4 and then 2, but the idea is the same. So what do? I read in the plots. For each plot, I read in the radius and remember that it's 4 times r squared. Same thing with the circular houses. And then same thing with the squares. But notice that I'm pushing all of them into the same vector, whether it's square or circles, because The square ones, after these calculations, I can pretend that they're circles. I sort them, both of them separately. And then I'm going to loop through. So plot I basically look at the current plot that I'm looking at in my list. And then I'm going to loop through my list of houses. And answer is how many houses I managed to assign. So this one, this little while loop basically says, wow, I haven't run out of houses yet. Sorry, I haven't run out of plots yet. And the plot that I'm looking at right now, it's too small for the house that I'm looking at. Then I increment it. So I skip over all the plots that doesn't fit the current house. Then after I get out of this loop, either I run out of plots to look at, or I find a plot that the house can fit in. So if I haven't run out, that means I can assign this house to this plot. So I increment the count, but also move ahead in the plot index so that I will not assign another house to this plot. And I just run this loop and then print the answer, and that's it. So this is I guess you can call it a greedy algorithm. For each house, you take the first one that fits. But in order for that to work, you need to sort it in a particular order so that it makes sense to go through them in that order and do the greedy solution. And then, of course, the other insight is that you can transform the square houses to circular houses and then do everything with no floating point computation by squaring everything. Okay, so that's the 5 easy problems, and I guess I'll make a video of the 5 harder problems later.